Hi students! Welcome to a second video tutorial on number representation. This lesson will enlighten you on binary addition, binary shifts, and 2's complement. Let's have a look at the contents of today's lesson. In this video lesson, we will discover the rules of binary addition, explain why overflow occurs in arithmetic addition of binary numbers, gain an understanding of logical binary shifts, learn how to represent positive and negative binary numbers using 2's complement, and we will wrap up the lesson with a recap. Now that we know binary numbers, let's learn how to add them together. In decimal addition, if we calculate 2 plus 8, we get 10, which we write as 1, 0. In the sum, this gives a digit 0 and a carry of 1. We already know the rules of addition we normally perform every day, that is decimal addition. We know how to handle the sums, carries, etc. Let's see how we would calculate the sum of 156 and 279. Note that in the units position, 6 plus 9 would give us 15. However, we cannot place 15 in this column since we can write only one digit below each column, so we regroup the number 15. For this, we write 5 in the units column and carry 10 to the next column, that is, the tens column. This one, called a carryover, is added along with the numbers in the tens column. So, 1 plus 5 plus 7 would give us 13. Leaving 3 in the current column, we would have a carry of 10 in the hundreds column. Finally, 1 plus 1 plus 2 would amount to 4. This addition would result in a value of 435. Binary addition is much like decimal addition. It follows a set of rules. Just like in decimal addition, we start by adding digits from the right. We add the first digits of a number, and if the count exceeds binary 2, then we carry 1 to the next row. Referring to these rules, let's see how we would add two binary numbers. 1 plus 0 gives 1. 1 plus 1 would give 0 with a carry of 1. Again, 1 plus 1 would give 0 and a carry of 1. Let's see if you have understood. Work out the given binary additions. These are the expected solutions. Go ahead and check if you can work out the addition of 8-bit binary numbers. Verify your solutions. Interestingly, the answer to the decimal addition and binary addition is the same. Let's consider an example. 1 plus 1 is equal to 2 in decimal addition. In binary addition, we get 1 plus 1 is equal to 1, 0, which represents 2 in the decimal number system. Let's try another example. Compute 0, 1, 1, 1 plus 0, 1, 0, 1. Using binary addition, the sum is found to be 1, 1, 0, 0. We can check our work by repeating the computation in decimal. 0, 1, 1, 1 is 7 in decimal. 0, 1, 0, 1 is 5 in decimal. 5 plus 7 gives 12, which is represented as 1100. Digital systems usually operate on a fixed number of digits. Addition is said to overflow if the result is too big to fit in the available digits, that is, when the answer to the binary addition is larger than what the CPU is capable of handling. For example, a 4-bit number has the range 0 to 15. 4-bit binary addition overflows if the result exceeds 15. The 5th bit of the sum is discarded, producing an incorrect result in the remaining 4 bits. Let us make sure that you have understood by trying out this question. Explain what is meant by an overflow error or overflow condition. This occurs when a calculation produces a result that is greater in magnitude than that which a given storage location can store or represent. Every computer has a well-defined range of values that it can represent. If during execution of a program it arrives at a number outside this range, it will experience an overflow error. It will occur when 8 bits are expected to represent a number greater than 255. As the name implies, a binary shift is just the shifting or moving of binary values. Binary numbers are multiplied and divided through this process. A bit shift moves each digit in a number's binary representation left or right. The bit shift is an important operation to perform mathematical operations efficiently. When performing a logical binary shift to the left, the bits shifted from the left end of the register are lost, and zeros are shifted in at the opposite end, that is, the right end. For example, 1011 becomes 0110 because the leftmost 1 is discarded and a 0 is added to the right. 1101 becomes 1010 after a left shift, as the original leftmost 1 has been discarded and a 0 has been added to the right. 1100 becomes 1000 since the leftmost 1 has been discarded and an extra 0 has been added on the right side. A shift to the left is equivalent to multiplying by a power of 2. The left bit shift moves every bit of the input one position to the left. In the example, we shifted the binary number 001100 or 12 in the decimal system 1 bit to the left. A 0 has been pushed in on the right end to fill up the bit succession. The result is 011000 or 24 in the decimal system. So, shifting 1 bit to the left is equal to multiplying a number by the factor 2. Shifting 2 bits means multiplying by 4, 3 bits by 8, and so on. When performing a logical binary shift to the right, the bits shifted from the right end of the register are lost, and zeros are shifted in at the left. To illustrate this, let's see the number 1100. After a right shift, the rightmost 0 is lost and a 0 is appended on the left. This changes the number to 0110. Likewise, 1011 has turned into 0101 as its rightmost 1 has been removed. 0011 becomes 0001 since it loses its rightmost 1 and 0 is shifted in at the left. A shift to the right is equivalent to division by a power of 2. The right bit shift moves every bit of the input one position to the right. In the example, we shifted the binary number 01100 or 12 in the decimal system 1 bit to the right. Thereby, the least significant bit is lost while a 0 is pushed in on the left end. The result is 00110 or 6 in the decimal system. So, shifting 1 bit to the right is equal to dividing a number by the factor 2. Shifting 2 bits means dividing by 4, 3 bits by 8, and so on. Time to check whether you have understood. The binary number 101 has undergone 3 left shifts. Part A. Work out the new binary numbers after each shift. Record the equivalent binary numbers. Here are the answers. Part B. State the effect the 2 shifts have had on the original binary number. The answer is that the original decimal number, which is 5, has been multiplied by 8 to obtain 40. In maths, when we need to write the sign of a number, we put the sign character at the beginning of the number. Unsigned numbers represent the positive ones, and we put the minus character at the beginning to represent the negative ones. However, in digital circuits, there is no provision made to put a plus or even a minus sign character to a number, since digital systems operate with binary numbers that are represented in terms of zeros and ones. If we want to write the number 3 in binary on its positive form, let's say in 4 bits, we would write 0011. Now, what happens when we need to write the negative form of the number in binary? I'll say it before, there is not the possibility to write the number as minus 0011. This is where 2's complement comes into play. 2's complement is a mathematical operation done on binary numbers. It is used in computer science as a method of signed number representation. This method uses the leftmost bit, called the most significant bit, as a sign bit to indicate if the number is positive or negative. When the most significant bit is 1, the number is signed as negative. If the leftmost bit is 0, then the number is either 0 or a positive integer. In the given example, the most significant bit is the 4th bit. Since it is 0, the number is considered to be positive. In this scheme, if the binary number 0011 encodes the signed integer 3, then its 2's complement 1101 encodes the inverse -3. In other words, the sign of most integers can be reversed in this scheme by taking the 2's complement of its binary representation. So, let's see how it works. The first step is to write the positive form of the number in binary. Secondly, we replace all ones by zeros and all zeros by ones to obtain what we call the ones complement. Finally, we add 1 with the result to get our 2's complement. Here are 2 more examples of how to use 2's complement to represent negative integers in binary. Let's see if you have understood clearly. Complete the table to show the ones complement and 2's complement of the given binary numbers. Verify your answers. If you are wondering why negative integers are represented in this strange fashion, the answer is that it makes arithmetic with signed integers easy for the computer to perform. This is best illustrated with a simple example. Consider the sum of the integers 12 and -3. To perform this addition, the computer would simply add the digits in the corresponding positions of the two 8-bit binary numbers. As expected, this is the 8-bit binary representation of the decimal number 9. This lesson has taught us about binary addition. We have seen that 0 plus 0 gives 0 and 0 plus 1 gives 1, similar to the denary system. However, 1 plus 1 in binary gives 1, 0. We discovered that the largest value a one-digit binary number can have is 1. As in decimal addition, if the sum of two numbers is greater than what fits in a single digit, we carry a 1 into the next column. We have seen that an overflow occurs when the answer to a binary addition is larger than the CPU is capable of handling. This results in an incorrect answer. A bit shift is an operation where a succession of bits is moved either to the left or the right. For logical bit shifts, the bits shifted out of the binary number's scope are lost, and zeros are shifted in on the other end. When a binary number is multiplied by a power of 2, there is a left shift of bits. On the other hand, when a binary number is divided by a power of 2, there is a right shift of bits. Finally, the lesson covered 2's complement, which provides a way of representing signed integers on computers. To convert the binary format to a 2's complement, we must replace the zeros with ones and ones with zeros. Then add 1 to the inversion to obtain the required conversion. This lesson has come to a close. I hope you have got a clear understanding on number systems. Thank you very much.